Hello friends, I am Professor Chinmay Deshpande from Zeal College of Engineering, and today we are going to see a topic of magnetism, basic concepts of magnetic material and its types. Before going in detail, what is actually a magnet? A magnet is the substance which possesses the property of being magnetized. A magnetic material are those materials which attracts ion filling towards itself. Nearly 600 BC, that is before Christ, this property was discovered at Magnesia Island, and that's why the name is magnet. This is the basic diagram of magnet, which consists of two poles, north pole and the south pole. The dotted lines which are shown around the magnet is nothing but a magnetic lines of force. Whenever any magnetic material is placed in an external magnetic field, it will create its own field around itself, which is also called as the lines of force or the flux. Now, we will move towards the basic concepts of magnetic material. First one is magnetic flux density. The definition of magnetic flux density is flux phi per unit area. Let us take a simple example. Suppose this is your area A1. How many number of lines will pass through area A1? Line 1 and 2. This is your area A2. How many number of lines will pass through it? 1, 2, 3. Means we can say that for your area A1, 2 will be the magnetic flux density, and for area A2, 3 will be magnetic flux density. The unit for magnetic flux density is Weber per meter square. Always remember one important point. The direction of magnetic lines of force is from north pole to south pole outside the magnet, whereas it is from south pole to north pole inside the magnet. Next one is magnetic field intensity. It is the degree or extent to which a magnetic material or substance can be magnetized in the presence of magnetic field. It is denoted by H or I. Next one is nothing but permeability of a magnetic material. Now if we see the word permeability carefully, there are two words which are present. First one is permission, that is permi, and second one is the ability. So simply we can define permeability of magnetic material as it is the ability of the magnetic material or the property of the magnetic material by virtue of which it allows itself to be magnetized. At what much extent it will allow to magnetize, depending upon this property, there are three types of magnetic material. Next one is susceptibility. Susceptibility is, again there are two words which are present, suck and ability. We know that whenever any magnetic material is placed in an external magnetic field, the magnetic force which is present gets sucked by that magnetic material. So we can define susceptibility as it is the property of the material which shows how easily a substance can magnetize. Your permeability is denoted by a symbol mu, whereas susceptibility is denoted by a symbol chi. Now depending upon these two important properties, the magnetic materials are classified into three types. First one is diamagnetic material, second one is paramagnetic material, and third one is ferromagnetic material. Let us move towards first type, that is diamagnetic material. The first type is diamagnetic material. The definition of diamagnetic material is that these are the substances which are weakly, that is feebly repelled by the magnetic field. Means we can say that they don't like the presence of magnetic field. Diagrammatically it can be represented as, suppose this is your diamagnetic material, then no magnetic lines will pass through it. As we studied right now, mu r is nothing but permeability. As no magnetic lines of force will pass through this, the value of mu r is always less than 1. Similarly, in case of chi, that is susceptibility, it is negative as no lines of force will pass through this. Now let us see the properties of diamagnetic material. Consider that first example. Here there are two magnets which are placed, north pole and the south pole, and suppose a rod of diamagnetic material is suspended in between these two magnets. What will happen? As they don't like the presence of magnetic field, that's why it will align itself in east and west direction. Means suppose this is north pole, this is south pole, and the rod is present in between these two poles. Then as soon as field is applied, it will align in this direction. This is north, this is south, so it will align in east and the west direction. Second property, consider that there is a U-shaped tube which consists of a diamagnetic material liquid. Whenever no field is applied, the level on both sides will be same. But as soon as field is applied to one end, as they don't like the presence of external magnetic field, this level will goes on decreasing and automatically this level will goes on increasing. Third property, let us see there are two magnets, north pole and the south pole. Now if these two magnets are placed very nearer to each other, then we can say that the field intensity is maximum at the center, whereas the field intensity is minimum at the corners. As diamagnetic materials are weakly repelled by magnetic field, here the presence of field is more, that's why accumulation will be less, whereas at the corner, due to less field is present, it will try to accumulate at the corners. Similarly, second example, if we place these two magnets very far away from each other, then field is maximum at the corner and it is minimum at the center. So it will try to accumulate at the center maximum. Examples of diamagnetic materials are aluminum, bismuth and copper. Next type of magnetic material is paramagnetic material. We can define paramagnetic material as the materials which are weakly, that is feebly attracted by the magnet. Means they like the presence of magnetic field. This is the diagrammatic representation of paramagnetic material. This is a paramagnetic material which is placed in an external magnetic field. Only few lines of force will pass through this. As it will allow to pass only few lines of force through this, its value of relative permeability is greater than 1, whereas the value of susceptibility is always positive in between 0 to some value. Again move towards the property of paramagnetic material. First property indicates that if we place a paramagnetic rod in between north pole and the south pole or in between two magnets, then it will align in the direction of magnetic field. That means the direction of paramagnetic material rod is in north to south pole. Second case, consider again U-shaped tube which is present. Now in this, whenever no field is applied, then the level will be same. But as soon as field is applied to one end, as they like the presence of magnetic field, it will increase, whereas it will decrease, it will move in the downward direction. Third property, again if we place a powder form paramagnetic material in the plate and if we apply a magnetic field to it, if the two magnets which are present are very close to each other, means what? At the center field is maximum, and as paramagnetic material likes the presence of magnetic field, so the accumulation of paramagnetic material powder will be maximum at the center, whereas it is minimum at the corners. Second one, if these two magnets are placed very far from each other, now at the corners field will be maximum and at the center field will be minimum. So it will try to accumulate more at the corner and less at the center. The examples of paramagnetic material are sodium, calcium and oxygen. Now let us see third topic, that is behavior of capacitor in the AC circuit. Consider that there is a one capacitor which is connected across a AC voltage source which is given by V equal to Vm sin omega t. Let I is the current which flows through the capacitor. So we can write the expression for the current flowing through the capacitor as I equal to C dV by dt. We know that what is the value of V? It is Vm sin omega t. So if we substitute here, the expression is C equal to or C into d by dt Vm sin omega t. Now what is the derivative of sin omega t? It is cos omega t. So the equation is omega c Vm cos omega t. We know that as per trigonometric formula, cos theta equal to sin of theta plus 90. So therefore here we can replace this cos omega t by sine of omega t plus 90. So your expression for the current becomes omega c Vm sine omega t plus 90. We know that omega c Vm is exactly equal to the maximum current, that is Im. So if we compare these two equations, this is your first equation, V equal to Vm sine omega t, and second equation, that is I equal to Im sine omega t plus 90, then we can say that your value of current leads the voltage by an angle of 90 degree. Here there is no any angle which is present, means omega t plus 0. Here current is omega t plus 90 degree. So from these two expressions, what we can say that your value of current I leads the voltage by an angle 90 degree. So this is what is your diagrammatic representation or a waveform representation. The first waveform represents voltage. Now what is the meaning of I leads the voltage by 90 degree? First current waveform starts, and after some time your voltage waveform starts. This is also a phasor diagram, as it suggests that I leads the voltage by 90 degree. So if we trace it in anti-clockwise direction, your current is leading compared with voltage having a phase angle as a phi. Means value of phi equal to 90 degree, and power factor we know that cos 90 is 0, so that's why cos phi equal to 0. Now what would be the value of impedance Z? Z equal to Vm by Im. Here we have substituted Im is omega c Vm. So if we substitute here, we will get 1 upon omega c, which is equal to 1 upon 2 pi fc. This is called as capacitive reactance. Means if in case of AC circuit your value of frequency will be 0, then the impedance will be exactly equal to infinite. So this is about behavior of capacitor in the AC circuit. Now we will move toward the combination of these three. Up till now we saw what is the response of resistance, what is the behavior of the circuit for the inductance, and what is the behavior of the circuit for the capacitance which is present. Now next one is serial RL circuit, which consists of combination of resistance and inductance which are connected in the series, and across AC voltage is connected, which is given by V equal to Vm sine omega t. Let voltage across resistance is VR, voltage across inductance is VL, V and I represents your RMS value. Now what is VR? It is I into R. What is VL? It is I into inductive reactance, that is XL. So we saw that in case of resistive circuit, the value of current and the voltage both are in phase with each other. So if we draw a phasor diagram, then value of current and the voltages both are in phase with each other, especially for voltage across the resistance. That's why we have written here VR. Whereas in case of inductive circuit, current lags the voltage by an angle of 90 degree. Now here we are tracing anti-clockwise direction. Current lags the voltage. The another way to represent this sentence is voltage leads the current. Means this is your value of voltage which leads the current by an angle of 90 degree. So this is your resultant voltage if we have connected resistance and the inductor in series, that is voltage V. This is your voltage angle or the voltage triangle. Now what is total impedance? We know that as per the diagram, V bar equal to VL bar plus VR bar. What is VR? I into R plus VL will be equal to J I into XL. So if we take current common, it would be R plus J XL. Now V divided by this I, if we have taken that term I to left hand side, then the next expression is V by I equal to R plus J XL, which is equal to impedance Z, that is Z equal to under root of R square plus XL square, or we know that XL is also equal to omega L, so we can write R square plus omega square L square. Now if I want to calculate value of phi, we know the formula, tan theta equal to y by x. So theta will be equal to tan inverse of y by x. Here y is omega L, x is R. So we can easily calculate the value of phi as tan inverse of omega L upon R. So in the exam, if we are asked the question to calculate the value of phi, then formula for this is phi equal to tan inverse of omega L by R. This is a waveform representation. The first waveform represents the voltage as it is RL circuit and as current lags the voltage by 90 degree. So in this case, as soon as your value of voltage reaches to the maximum, that is 90 degree, then at that point your current waveform starts. Now we will see third circuit, that is combination of resistance, inductance and the capacitance. What will be the behavior of RLC circuit? Consider that resistance R, inductance L and capacitance C is connected in the series across which AC supply is connected, which is given by V equal to Vm sin omega t. Now what would be the voltage across resistance VR? It is equal to current flows through that and value of R. So VR equal to I into R. What will be the voltage across inductance VL? It is I into XL. XL is the inductive reactance. What will be the voltage across capacitor VC? It is I into XE, where XC is the capacitive reactance. Now this is the short form which we need to remember. In case of R circuit, I is the current which is in phase with the voltage. In case of L, that is purely inductive circuit, current lags the voltage by an angle of 90 degree, whereas in case of capacitive circuit, current leads the voltage by an angle of 90 degree. So now there are two cases in case of series RLC circuit. The first case would be if your inductive reactance is greater than capacitive reactance, means your total circuit is of having inductive nature, that is RLC circuit. So in that case, no presence of XL, assume that. So in case of resistive circuit, voltage and current are in phase with each other. So that's why I and VR are in phase. Whereas in case of inductive circuit, we saw here, in case of inductive circuit, I lags the voltage by 90 degree. Means if we trace anti-clockwise direction, then I lags the voltage across the inductor by an angle of 90 degree. So that's why we have drawn here voltage, the phasor is like this, upward direction. Now the vector addition is nothing but a total voltage V. This is a waveform representation in which again it is voltage waveform as current lags the voltage by 90 degree. So whenever voltage reaches to 90 degree, current waveform starts. So this much amount of distance between these two waveforms will be exactly equal to your angle, that is phi. Case B will be XC is greater than XL, that is it is only a capacitive circuit. Now we know that in case of capacitance, current leads the voltage by an angle of 90 degree. So that's why here again same current and VR will be in phase, as in case of R circuit both will be in phase with each other. But as it is capacitive circuit, XC is more compared with XL. So therefore now current leads the voltage by 90 degree. That is, if we trace anti-clockwise direction, then current leads the voltage by an angle of 90 degree. Resultant will be this V bar equal to VR bar plus VC bar. So this is waveform representation. So here for simplicity we have drawn voltage waveform here, and as current is leading the voltage by an angle of, means first current waveform will be start and after some time, that is a delay of angle phi, voltage waveform will be start. So this phi is nothing but angle between voltage and the current waveform. Now what would be the total impedance? V equal to VR plus VL plus VC. In terms of current, it is VR equal to I into R, VL will be equal to I into JXL and VC will be equal to I into minus JXC. So V bar upon I bar, if we have taken I common from this and I is shifted to the left hand side, then right hand side will be equal to R plus J XL minus XC, which is equal to impedance. So we can calculate Z equal to under root of R square plus XL minus XC square. If we want to calculate angle, then phi equal to tan inverse of Y by X, that is XL minus XC upon R. This is what is impedance triangle. Now from that we have drawn impedance triangle. Z is taken as a hypotenuse. This is A side, this is B side. Now as XL minus XC will be positive, so that's why we have drawn like this. This is your R, this is your XL minus XC, so resultant will be equal to Z for XL is greater than XC. Whereas in case of second, that is XC is greater than XL, as capacitive is more means your negative part is more, so that's why we have drawn nature is like this. So Z equal to R square plus XC minus XL square. So in that case, this is nothing but your XC minus XL as it is along Y axis. This is X axis, that's why we have written here R, and resultant of this is nothing but your Z, and phi is angle between, that is phase angle between voltage and the current.